So far, we've derived quite a lot of differentiation rules, and specifically I've pointed out how chain rule will be crucial to tackle more complex functions, functions of functions, or composite functions. And you will be using chain rule throughout your degree. There are still some functions that you will not be able to differentiate right away with the rules that we've derived, but for which we can use some tricks and manipulations in order to differentiate them. One of such tricks is logarithmic differentiation. Let's have a look at that and also tackle a practical example of how you can use it. Let's say you want to take the derivative of a function that is given by y equals x to the power of x. We've seen how we can differentiate using the power rule, but that only applies when you have x to the power of a real number, not x to the power of a variable itself. With the rules that we've covered, we cannot differentiate this. However, with logarithmic differentiation, we can do this, and this is a useful technique whenever you have x to the power of something that depends on x. How do we do it? Let's look at the name and take logs, natural logarithms, to both sides of this expression. If we get to this stage, the great thing about using logarithms is that we can take the power out. So we can also write this as ln y equals x, ln of x. And this is the thing that's really helpful for us to be able to differentiate this function. When we get to this stage, what we do is we differentiate both sides. This is okay, we're keeping the equality and just applying d dx to this part and d dx to this part. When we get to this stage, we need to realize two things. The derivative on the right hand side is relatively easy. This is just product rule, and also we know how to differentiate ln of x. That's easy. On the left hand side, we need to be careful because, as we can see here, y is a function of x, and therefore to differentiate this part we need to use chain rule. By using chain rule, we can write that the derivative of ln y in respect to x is 1 over y times dy dx. This is using Leibniz notation, and again pointing out that this is the case because y is a function of x. We don't know what it is. Well, in this case we actually do, but we don't even know what the derivative is. This is what we're trying to calculate. So whenever this happens, and this will be crucial for one of the next topics, which is implicit differentiation, whenever you encounter something that is a function of the variable you're differentiating against, you need to keep dy dx. The other side is just product rule. So we have 1 over x times x plus 1 times ln of x. We can then simplify this, so this just becomes 1, which means we can write this as 1 over y dy dx equals to 1 plus ln of x. Remember that what we want to find out is actually this. We want to find out what dy dx is, or the derivative of y. All we have to do here now is take y to the other side, which means multiplying by it. And in these cases, and for logarithmic differentiation, typically you can write y as a function of x, and if you end up having a y, it means you can sub it back in to get your final answer, which means the final answer is 1 plus ln of x times x to the power of x, which means the derivative of a function x to the power of x is given by 1 plus ln of x times x to the power of x. And in principle, if you do encounter this, you could use this directly, but it's really useful to understand logarithmic differentiation because with simple steps such as applying logs so that you can drop the exponent and then differentiating left, right, manipulating, you get the answer. To make sure you're fully on board, let's try another example. Let's say that you want to differentiate this function. You can find this also on the lecture notes in section 5.7. You may ask though, why do we need to use logarithmic differentiation? The answer is very simple. You do have something which looks like a function of x to the power of x. Therefore, there is no simple rule that you can just apply straight away. But in these cases, always try logarithmic differentiation. If you followed what I just told you, you know that step number 1 is applying logs to both sides. When we get to this stage, it means that we can use the properties of logs to make your life easier. There is a product, so we can split the natural logarithms, and also the reason why we're using logarithmic differentiation is to be able to deal with the power of x. Let's do it then, which is sort of step number 2 of logarithmic differentiation, is using the properties of logs to make your life simpler. There are of course many ways you could do this. You could choose to keep these terms together. It doesn't really matter. But now once you get to step 2, you are ready to take derivatives of both sides. And remember, you're differentiating the entire right-hand side and the entire left-hand side. Once you get to this stage, it is a very similar process. The derivative of ln y will be given by 1 over y dy dx. That is because y is a function of x. Again, this will be crucial for implicit differentiation. And the other side, the reason why I split it this way, so that we know that this is 0, you can even write it, it doesn't really matter. The derivative of ln of x is 1 over x. Here we're going to use product rule, and I'm going to do it slowly and explaining all the steps just to make sure I don't lose you. What we're going to do first is multiply x over 2 by the derivative of ln cos of x. And the only thing to note is that this is a composite function. Therefore, we need to use chain rule. The derivative is something like 1 over cos x times the derivative of cos x, which is minus sin x. So it means that instead of using a plus, I will lose directly a minus x over 2 sine x over cos of x. We've used chain rule here. And we also need the other term, which is ln cos of x times the derivative of x over 2, which is just 1.5. So I'll write 1.5 times ln cos of x. Since there's not a lot of space remaining, a little bit of good old physics 101 magic will help. We can now continue this. I'll do it over here. The next step is similar to what we've seen before. We're going to take y to the other side. We can then replace it, and we have found our final solution, which means that dy dx is equal to 1 over x minus x over 2 sine x over cos x. Let's call it tan x. Makes your life easier. There's less things to write. Plus 1.5 ln of cos x. And everything will now be multiplied by 7x cos x to the power of x over 2. That's 7x cos x to the power of x over 2. When you get to this stage, sometimes it helps to simplify it, just to make it less ugly, less of a huge train. In this case, Maybe the only thing you could do would be to take the 1.5 here out and group them, but it won't really help you that much. So it is okay to leave your answers like these, and this will be crucial also for implicit differentiation. In some cases, you can make it look quite tidy and neat. In most cases, it will look relatively ugly, and that is okay. You don't need to simplify it in general, unless it is obvious. In this case, it is not obvious. The only thing that actually we did was to transform sine x over cos x as tangent of x. The other advice for logarithmic differentiation, again, is to practice. If you practice and if you understand the steps, go back in the video. Step number 1 of just applying logarithms to both sides, then using the properties of logarithms to make your life easier, then differentiating both sides, manipulating, taking y to the other side, and then replacing what y is in terms of x. If you've mastered that, I think you're definitely ready for the next topic, which is implicit differentiation. See you in the next video.